This lesson is for section 1.7 in our textbook, Symmetry and Graphs. First, I'm going to start with a basic introduction to symmetry and reflections. 2 points, A and B, are said to be symmetric to one another with respect to line L if line L is the perpendicular bisector of the line segment joining the points. So, what that means basically is if we were to construct a segment connecting A and B, and line L happens to be the perpendicular bisector of AB, then A and B are symmetric with respect to line L. Reflections are kind of like a mirror. So your line acts as a mirror, and in this case, if we were to reflect about the x-axis, our new image looks like this. So you can see that the points x, y now turn into x comma negative y. So if you look here, we now have x as the perpendicular bisector, because if we connect any point, the x-axis here acts as the perpendicular bisector between any 2 points on this image. So it's still the same idea here as symmetry as well. Now a reflection about the y-axis now flips across the y-axis like so, and every point x, y now becomes negative x, y. A reflection about the line y equals x looks like this. We'll talk about that a little bit, but most importantly we have the x and y-axis reflections, as well as the next one, the reflection about the origin. So this time we're reflecting it about a point. We don't see a line here, but when we reflect about the origin, we reflect over the x and the y-axis. So let's take our example here and first flip this over the x-axis. So we result here with this purple image, and if we reflect it again about the y-axis, now it becomes, like here's our original as well as our new image. All the points x comma y now become negative x, negative y. Now if you reflect over the y-axis first and then over the x, it still becomes the same image. So here we have it reflecting over the y-axis and then flipping now over the x-axis, and you can see here that our resulting image is still the same. Okay, let's bring it back now to our note sheet. So I would like you guys to try to reflect this point A about the x-axis, the y-axis, the origin, and the line. So I want you to check your answers to this portion here, because I'd like you to try to complete this as well. And I kind of alluded to this in the video, talking about what x, y becomes once you create that reflection about the x-axis or whatever axis you're looking at. So please pause the video and then come back and we'll talk about each one of these. It might help to label this point here as 2, 1, and then when you create your reflection, see what your resulting point becomes. Okay, let's begin with the reflection about the x-axis. So if we take a look at these coordinates, the point 2, 1 has now changed to 2, negative 1 after we apply this reflection. So x, y now becomes x comma negative y. Therefore, just by substitution here, I'm just going to plug this in here, okay, negative y equals f of x now becomes negative y equals f of x. Now if I want to solve for y, another way of saying that is y now becomes the opposite of f of x, so negative f of x. Now, in a reflection about the y-axis, the point 2, 1 became negative 2, 1. In other words, xy now becomes negative xy. So again, by substitution here, I'm going to substitute these values in. Y now equals f of negative x. When we reflect about the origin, the point 2, 1 became now negative 2, negative 1. So the point xy now becomes negative x, negative y. And by substitution here, let's plug this in. So negative y equals f of negative x. Solving for y, we end up with negative f of negative x. Now in the last one, with respect to the line y equals x, the point 2, 1 now became 1, 2. In other words, xy became y comma x. So by substitution here, x now equals f of y. So this translation or this reflection here isn't one that we talk about a lot. This one in particular, with respect to the line y equals x, we focus mostly on the x-axis, the y-axis, and the origin. Okay, you could either try to pause here and come up with your answer for number 1 on your own. It's a good thinking question, but basically we're going to try to take the point 2, -3, and we are going to reflect this point about the y-axis. So if you recall, if you reflect about the y-axis, f of x equals y now becomes y equals f of -x. So if we look at our beginning coordinate here, we now have the point -2, -3. Okay, because once we apply that the reflection here, we now have the opposite value of x. So if you think of it visually, you start with the point 2, -3, so somewhere like right here, and you apply a reflection about this axis here. This is going to switch over to this side. Now you have negative value for x, so -2, -3. Now if you take that same point, you can do this visually, and you reflect about the x-axis, so we have this point here, we're reflecting it now about this line. The point becomes still same x value, but -2, 3. So in other words, y equals f of x now becomes opposite, right, of y. So y equals opposite of f of x. And the point now becomes -2, 3. Okay, now in problem number 2, it says the range or possible y values of q of x is -2 is less than or equal to q of x is less than or equal to 12. So what is the range of the opposite of q of x? So, or negative q of x. So we have to figure out what kind of reflection this is. So recall that when xy becomes x negative y, this is f of x, y equals f of x, now becomes y equals the opposite of f of x. So this is what our reflection is, and this reflection here is the reflection over the x-axis. Okay, so what we're going to do here, I'm just going to multiply -1 throughout this range here, and I get +2. That sign flips. The sign over here flips as well. And so I want to rewrite that as -12 is less than or equal to -q of x is less than or equal to 2. Now if I want to write this in interval notation, I should have a closed bracket and another closed bracket, and there's my answer. In problem number 3, you have a table with a function f of p, which equals p squared plus 2p minus 3. So they give you the inputs and the outputs for p and f of p. And now they ask you to complete the chart if you're given these two rules. So if g of p equals f of -p, try to figure out which reflection this is, and then fill out your resulting chart here. Same thing with the second chart. If h of p is equal to -f of p, figure out what type of reflection this is, and then fill in your resulting chart. Okay, so let's fill out this table. So, looking at our rule here, g of p is equal to f of -p. So that means when I know that p is -3, I actually want to look back here at the opposite of p, which is going to be 3. And I look here, and f of p is equal to 12, so g of p should equal 12. So you're looking for the opposite in f of p, basically. Alright, so -2, I should have 5. For -1, looking here, it'll be 0. For 0, it's going to be -3. For 1, we're going to look at -1. For 2, we'll look at -2. And for 3, we look at -3 to get 0. So there's my table. For h of p, I do the same thing. So here, the rule is h of p equals the opposite of f of p. Here, we're going to take all values for f of p and change them to their opposite. So h of p, we plug in -3, we're going to get the opposite of 0, which is still just 0. For h of -2, we look here at f of -2, and we take the opposite, so we get 3. Taking the opposite here, we get 4, +3, 0, -5, and -12. Okay, so based off of these two things here, we look, g is actually the reflection of f, right? It's the reflection of over the y-axis. Okay, this follows our rule. y equals f of x becomes y equals f of negative x. Okay? Now h is the reflection of f over the x-axis. And I'm getting a little cluttered here, so let me erase. So if we look at our rule here, h of p equals negative f of p, this follows our rule that y equals f of x becomes y equals negative f of x when reflected over the x-axis. So really our basic main ideas here, ones that are most important, are going to be that y equals f of x becomes y equals negative f of x when you have a reflection over the x-axis. These are the big ideas here. When you have a reflection over the y-axis, you end up with y equaling f of x becoming y equaling f of the opposite of x. When you rotate about the origin, or reflect about the origin, y equals f of x becomes negative y equals f of negative x, or y equals negative f of negative x. So these are your three main ideas for reflections. So we're now going to take that idea about reflections and apply that to symmetry. So we say that a curve is symmetric in the xy plane with respect to the y-axis here. So I have a picture of a parabola, and this is reflected, or it's symmetric about the y-axis. So if you see, every point on this parabola has a point that's been reflected about the y-axis. So it's symmetric about the y-axis. So here, our symmetry, we call this even symmetry when it's reflected about the y-axis. So here we have a parabola. This is our function, and let's take y equals x squared. The algebraic test to determine whether or not your function is symmetric about the y-axis is to actually replace, if you look here, all of the values x and negative x should be able to be replaced. So if you can replace f of x with negative f of x and your function is still equal, it's passed the algebraic test to determine whether or not it is symmetric about the y-axis. So I'll do a quick example of that. Here, in number 4a, it asks what type of symmetry x squared plus y squared equals 16 has. So if we want to check if it's symmetric about the y-axis, we are going to plug in x as now negative x. So when I plug this in, if I get the exact same outcome, x squared plus y squared equals 16, then I know that it's symmetric about the y-axis. So I plug in negative x, and I still get the exact same function that I started with. So this is reflected, or it's symmetric about the y-axis. Now a function is symmetric about the x-axis. Let's skip to over here. This actually is not a function. It's actually a relation because it doesn't pass the vertical line test to be considered a function, but we'll talk about that a little bit later. So where it says function, this is actually an absolute value relation. But this is symmetric with respect to the x-axis, because if you see here, every point has been reflected over the x-axis. So the algebraic test for this is going to be to check, is f of x equal to negative f of x? Okay, so I can go back to that same example that we were just working on. So we determined already that it has symmetry about the y-axis. So now let's check if it's symmetric about the x-axis. So if it's symmetric about the x-axis, that means that we should be able to plug in for f of x negative f of x. In other words, y equals negative y. We're going to substitute y in for negative y. So x squared plus negative y squared equals 16. If it is symmetric about the x-axis, we should get the resulting same relation, and we do. These are the same. So this is also symmetric about the x-axis. Now the last one, let me fill this out. So Let's see, this was an absolute value relation. The symmetry was about the x-axis. There we go. Okay, now for the origin, if it's symmetric about the origin, and if you look here, the points x, y now become negative x, negative y. And in this case, we have the cube root function here. And it's y equals the cube root of x. Now, the algebraic test here is to determine if f of x is equal to negative f of negative x. So, coming down here, if you want to test the same thing about the origin, now we replace x with negative x. We also replace y with negative y. So, if negative x squared plus negative y squared is equal to 16, which it still is, then this is also symmetric with respect to the origin. So this circle, this is the graph of a circle, is symmetric to all. You can kind of tell if you were to graph a circle here. You can see that it has even symmetry about the x-axis, the y-axis, as well as the origin. Okay, so to recap, if we want to test whether or not a function is symmetric about the y-axis, then we're going to check to make sure that x, when we replace x with negative x, we get the exact same expression. Okay? If we want to check to see if it's symmetric about the origin, we take x, we replace it with negative x, and we take y, we replace that with negative y, and we check to see if we get the exact same equation that we started with. When we want to check to see if it's symmetric about the x-axis, we replace y with negative y. Okay, in problem B here, we want to again check to see if it's symmetric with respect to the x, y axis or the origin. So I kind of changed the order here, but for the x-axis, I want to check if I replace y with negative y in my equation, do I get the exact same equation? So if I do that, plugging it into here, I have negative y equals 4x to the 7th minus 3x to the 5th. I'm going to solve now for y. So that means I would divide the negative 1 here, and it would change my function to y equals negative 4x to the 7th plus 3x to the 5th. So because these are not equivalent, this is not symmetric about the x-axis. Okay? So now we test the y-axis. If it's symmetric about the y-axis, then I should be able to replace x with negative x and get the exact same resulting equation. So here, again, I'm going to erase a little bit. Here I test and plug in, so if y is equal to 4 times negative x to the 7th minus 3 times negative x to the 5th, and I simplify here, if I get the exact same equation, then it's symmetric with respect to the y-axis. So let's test it out. When I take negative 7 negative x to the 7th power, I still get negative 4x to the 7th. And here, when I take negative x to the 5th, because it's an odd power, I'll still get a negative, so that becomes positive 3x to the 5th. And as you can see, this is still not the original equation, so this is also not symmetric about the y-axis. Okay, now our last test is for the origin. So for the origin, I want to change x to negative x and y to negative y. So I replace both of those in the original equation and solve again for y to see what I get. So I now have negative y equals 4 times negative x to the 7th minus 3 times negative x to the 5th. And if I solve, let me simplify first and then I'll divide out that negative. I get negative 4x to the 7th and positive 3x to the 5th. But I still have to get rid of this negative sign, so I'm going to divide out that negative to get positive 4x to the 7th minus 3x to the 5th. So as you can see, I get the exact same equation that I originally started with, so it is symmetric with respect to the origin. Okay, so I would like you guys to try the rest of these problems on here and then check your solutions with the answer key. So some of these are a little bit, just a review of what we've been talking about. So finish here and 5 and 6, and you can stop with this part and then move on to the second part of the notes.